Benny Tayono. I'm the chair of this conference. And before we move on to the main session of the conference, I'd like to introduce the program for you. I'm very pleased that this year's workshop we have 24 presentations split into two streams. The new things for us this year, we have practitioner sessions and also software vendors sessions or presentations. As usual, you'll have, I'm sure you've seen this morning also, sponsors, exhibition and posters. So please, when you have time this afternoon during the break time, please have a look and have a chat with the authors of the posters. And to start with today's event, Barry Nelson will give the keynote speech. And tomorrow we'll have panel discussions. Simon Taylor will lead that panel discussion with, the topic is simulation and analytics. And of course we'll have a conference dinner tonight. First of all, let me thank you for contributing to this conference, all the authors, the presenters, scientific committee members, and also the reviewers. Again, thanks very much for your time and effort. My special thanks to the sponsors, the STL, Lana, Polgrave Macmillan, Seeker Solutions, DSC Consulting, and Simulate. I'd like to, first of all, again, thank Hilary for organizing this the conference. Hilary is from the OR Society. Of course, my team, program chairs, Stefan Ongo. Would you please stand up? Thank you. And Carl Kiwi. Publicity chair, Joko van der Zee. Thank you. Poster chair, Tom Monks. And I'm grateful with the support and trust given by the advisory board, Stuart Robinson, and of course, Simon Taylor. Last but not least, of course, I thank the members of the panel discussions, Barry Nelson, Mark Elder, Ken McNaught, and Christine Curry. Thank you. As you probably, if you attend this workshop 2 years ago, since 2008, I believe, we announced the award for the best paper published in Journal of Simulation. And to present the award this year, I would like to invite Stuart Robinson, President of the OR Society.
First of all, actually, it's a slightly odd role for me, this, because the President of the OR Society always comes along and says, welcome to this conference. And yet this is the conference that I'm sort of always at anyway. But first of all, from the OR Society, I would like to say welcome to everybody. You should be aware the OR Society is the society that actually sponsors and organises this conference, particularly Hilary, who you met at the door, puts a huge amount of effort into organising this particular event. Just a couple of things to sort of anniversaries, I suppose. One is just to mention that the OR Society is actually 60 years old as of November last year, so we're currently celebrating the 60th anniversary of the Society. Some of you may be scratching your heads and trying to work out, oh, I thought it was older than that. Officially, there was an OR club prior to that, which I think, unless you were bald and male and wore a suit, you weren't allowed to join. In fact, was if you see any pictures from the late 40s and early 1950s. I'm going that way, yes, I'm being told. So just a bit of hair. But in November 1953, it was decided to make it a society that was open to all. So this is the 60th anniversary, and it's the oldest OR society in the world. In terms of this conference, you'll notice this is the 7th simulation workshop. We run it every 2 years, so this is actually, it's 12 years ago since we first started this conference, and it was Simon and I who, it was Simon who had the vision for the conference, and me who said, oh no, I don't want to do that. And I never forget, we met the first time at the conference facility at Birmingham University, and I think we had about 65 people, which was quite a shock to us at the time. And I never forget, Simon and I, just before we started this session at that conference, we looked at each other and said, what have we done? So, which is, and I'm glad to say the conference has continued from there, and I think has always been a really good opportunity for the community to meet, to discuss simulation and latest developments in that. I'll also mention, what we're coming to really is the Journal of Simulation. It's in its 8th issue, is it, Simon?
That's right.
Yep, so Simon is still, I'm no longer editing it, but Simon is. And I think the key thing with the Journal of Simulation since we last met at this conference is it now has an ISI rating. Ask Simon for the actual number. I can't remember, but for 0.74, yeah, which we were very pleased with. For academics, you'll understand the importance of that. If you're not an academic, you probably think, what am I talking about? It doesn't really matter that much, is what I should say, but it's a measure of the rate at which people are actually citing works from the journal, and I think for such a young journal, it's done extremely well to get that rating at that level. We launched the KD Tocker Award, was it 6 years ago, in memory of KD Tocker, who developed the first simulation software, and that was itself in the early 1960s, and in fact late 1950s, which was the 50th anniversary in 2008 when we launched this award. So the award that we set up was in memory of KD Tocker for the best publication in the Journal of Simulation. Unfortunately, this year the actual award winner isn't able to be at the conference, so all I'm going to do is tell you who it is rather than make a huge announcement. But Jabba Bohr and Ivo Sarnen paper from 2012 is the winner on this occasion for a paper called Improving Container Terminal Efficiency Through Emulation. And you can find that in the 6th volume, the 4th issue of the Journal of Simulation from 2012. Jabba actually came over to the UK in November to the OR Society's Blackett lecture and received the award on that occasion. So he was over for receiving that award. So congratulations to them. And at this point, I'm going to hand back. Where's Benny gone? He's running out the room. Over to Benny.
Thanks, Stuart. Right, before moving on to the keynote talk, I just want to have a quick message from Joss. We would like you to recommend to your library, if possible, or promote it to your colleagues, and write a paper to this journal, or receive it in print if you want to. So please consider your paper published in this conference and extend it further and send it to Joss. Right. Next, of course, I would like to invite Barry Nelson to give the keynote talk. Barry Nelson is the Walter P. Murphy Professor and Chair of the Department of Industrial Engineering and Management Sciences at Northwestern University in the US. Barry's research is on the design and analysis of computer simulation experiments on models of discrete event stochastic systems with applications to manufacturing, services, finance, and transportation. Barry has published numerous papers and 3 books, including Discrete Event System Simulation and Foundation and Methods of Stochastic Simulation. So I'd like to welcome Barry, and thank you very much for attending this event.
Okay, thank you for having me. I've got.
You got yours. Right, okay.
I'm looking forward to the sessions. This is not the usual group that I attend conferences with, and I look at the program, and I think there are lots of new things that I'm going to learn at this conference. So it's a really nice opportunity for me to get to come. I do apologize. I'm recovering a little bit from a cold. I sound just like the actor George Clooney when I don't have a cold, but this is what I'm going to sound like today. And so I want to talk a little bit about why good simulations go bad. So how does a talk like this come about? Well, some of the sort of foundational experiences that I had. The first time I ever heard anybody call anything computer simulation was in a computer methods class that I took as an undergraduate. And we simulated simulation of a dog chasing a runner. It was a system of differential equations we numerically integrated through time. And since I was a member of the track and cross country team at my university, I immediately knew that simulation was useful and something I wanted to know more about. The first real simulation class I had was in graduate school from the late Alan Pritzker, and shortly after I had that class, I was working on a project for the United States Air Force. It was called the HEART Project, and the idea was to try to reduce the incidence of cardiovascular disease among Air Force pilots. Hard to believe in those days that pilots not only smoked, but were almost encouraged to be smokers, and the Air Force realized that was causing serious problems. And my job was to design the screening and risk reduction facilities. So that was the first time I encountered a real system with real data and real decisions that were going to be based on the results of the simulation, and it was the first opportunity to make real mistakes. And so lots of what I'm going to talk about today really literally come out of that first project that I had. Now, not too long after that, I bought my first what might be called a personal computer, a Commodore VIC-20, and in between playing video games, one of the things that I did was code up an animation of an MM1Q, and the graphics were not even quite that good, but I remember that I knew lots of mathematics about queuing, but I would never have recognized that kind of behavior if I'd seen it out in the field without having done simulation. And so the other thing I really realized very quickly was that simulation was great for intuition building. Now, I am a true believer in simulation, and I think it's a great time to be a true believer. Certainly in the US, simulation has never been more used and accepted than it is right now. And as I'm sure you're all aware, the software we use is cool, pretty, and intuitive to use. It really makes it a lot easier to build models and also to sell our results. There's a big emphasis on analytics, and I think the emphasis on analytics can actually increase the use of simulation, although we'll probably need to slant our emphasis more towards decision support as opposed to system design, which has kind of been our traditional strength. But that's something we're going to talk about in the panel tomorrow, and so we'll see if you agree by the end of that. And simulation is increasingly being integrated into other tools as well as being a standalone analysis tool. And it's really not too far-fetched to think of simulations building themselves from the data in an enterprise management system. And I was going to mention here an experience I had like that, but I noticed there's a great paper this afternoon, I want to get the title right, towards automated simulation input data, which is very much on this kind of topic of automatically building at least part of a simulation model without a lot of human intervention. And that certainly would be useful for us to be able to scale up, simulating large-scale systems and making a lot of impact. So this is all good, but I also worry. Now, partly that's just my personality. I'm a worrier, but these are some specific things that I worry about. Why good simulations go bad. Now, what I mean by good simulations are simulations that are used in an appropriate setting, so it's really a simulation problem or a problem the simulation can solve. The model is a well-developed model, appropriately validated, in every sense appropriate for the situation, but somehow we still don't get everything that we're supposed to get out of that simulation. And so at a very cryptic level, these are the things I'm going to talk about today. Simulation is risky business. Yes, that's a young Tom Cruise there from a famous film. The ghost of R.A. Fisher. Simulators don't clean up their messes, and everything I told you is wrong. Not what I told you today, but everything I told you before today is wrong. In the U.S., there's a very popular radio comedy quiz program called What Do You Know? And they always start the quiz with the 4 disclaimers. So here are my 4 disclaimers. First, this is not a research talk, because research emphasizes things that are exceptional. And what I'm going to talk about are things that are very common, that occur in many, if not most, simulation studies. The opinions expressed here are my own and cannot be blamed on the workshop organizers. Nevertheless, they are well-reasoned and insightful. This is the part that I stole from the radio quiz show. That's one of their disclaimers. The talk is a little bit preachy. I'm talking to a simulation group, a sophisticated simulation group, and so I'm not telling you that we do things wrong as a general rule, but I think that some of the issues that come up here, I find myself making these kinds of mistakes or shortcomings, and so I think it's worthwhile at least for us to think about it. And I am carefully not plugging anybody's software, because software is obviously very important to what we do. It's critical in simulation, but it's also a competitive world out there, and so while I'm going to run some simulations here, they're all little things that I coded up in Visual Basic just to make sure that I'm not stepping on anybody's toes when talking about the software. Okay, so the first topic is simulation is risky business. Now this will be the longest of the three. The way I've organized it is each of those four will be a little less lengthy than the one before, realizing you'll be more and more impatient for the break. And the way I'm going to do this is I'm going to start with an example in which none of us would ever have made any sort of mistake. We would have gotten everything we'd intend to out of the simulation. I'm going to creep towards something that's a little more subtle. So Highlight is a handball-like game that's played in Florida in the U.S. and on which you can bet. So it's like horse racing or something like that, but it's pari-mutuel betting, which means that the house takes their take off the top. They don't care what kind of sophisticated methodology you use to try to win because you're betting against the other people who are there. This actually started in the Basque region of Spain, as well as called Basque Pelota, but in the U.S. I think is the only place on which there's still active betting on Highlight. Now here's the way the game goes. There are 8 players in a match, and you're going to bet on one of those players. There are complicated combination bets, but let's just talk about the simplest bet, which is betting on some player to win. So you can think of the 8 players as being in a line. The first 2 players come out on the court. They fling an amazingly hard ball at a wall and try to do it in a way so that their opponent can't return it. The player who wins the point stays on the court. The loser goes to the back of the line and waits to play again. Player number 3 comes out. They play point. Winner stays. Loser goes to the back of the line. The first player to get to 7 points wins. Now, if it worked exactly the way I just described it, it would be quite clear that the players at the end of the line were at a significant disadvantage, right? Because lots of points have been won before players 6, 7, 8 ever got out on the court. So the scoring system, which for marketing purposes is called the Spectacular 7 scoring system, corrects for that in the following way. It says there's 1 point per win for the first 7 games and 2 points per win after that. Right, so 1 point for the first 7 turns of the game, and 2 points per after that. And of course, that evens out all the odds. Yeah, well, does it? And so this example was stolen with great thanks from a book called Calculated Bets by Stephen Skeena. I highly recommend it, particularly if you want to get students interested in computer simulation and operations research. It's a very well-written book. He uses this as one of many examples of dealing with risk. All right, so how would a simulation person go about deciding if the Spectacular 7 scoring system actually works? Okay, so does starting position matter? So if your favorite player is in position 4, for example, should you bet high or bet low? What should you do? Well, the first thing you do is say, okay, let's take players out of the game. Let's suppose all players are equally good. So if all I'm trying to do is decide if starting position matters, it's like a coin flip. Whether player 1 or 2 wins, probability 1/2. Now, of course, what all of us are very good at is we can build an algorithm in a computer language to simulate the rules of Highlight. Well, I gave you all the rules on the previous slide, so it's a pretty simple simulation to do. Of course, we get very tired of flipping coins, so we let pseudo-random numbers stand in for the coins. And then we run lots and lots and lots of matches of Highlight to see what happens. So let's do that. So this is our first demonstration, pardon me. Oh, let me explain a little bit before I get started. So we're going to run a little simulation here. The players are listed across the top, players 1 through 8. As we run the simulation, the percentage of wins is going to show up here. And because these are estimates of the probability that a player wins by position, of course they have error. And so I'm going to display error there as plus or minus, right, a 95% confidence interval on that. So here you can see I simulated 1 game. It turns out player 4 number 1, but of course we know that one round of this doesn't tell us anything, and so we need to do. Sorry, I'm going to do that to you several times. All right. I did videos because I was really afraid I'd be too nervous to actually type. All right, so now it's running. This is going to do 5,000. We could just as easily do 50,000 or 500,000 because it doesn't take very long, but for the purpose of a talk, that'll be enough. And you can see the wins being racked up along here. You can see the percentages of changes, and you can see the error going down, right? As we do more and more highline matches, our error in the estimate that a player wins by position goes down, and here we've stopped. Now at this point, we've estimated the probability that you should win by position to about plus or minus 1%, so pretty good in terms of the estimate. And it's really, really clear that the spectacular 7 scoring system doesn't work. Right? In fact, it doesn't work very well at all. Player 1 and player 2 have a significant advantage, particularly over player 7. Right? Player 7 is a really, really poor position to start with, and so if your favorite player is stuck in position 7, don't bet on that round, because it's going to make a lot of difference. Now, none of us in this room, even though we've estimated these probabilities very precisely and could certainly estimate them even more precisely, none of us would be willing to bet our entire pension or next month's paycheck or next term's tuition on one bet of highlight. Because even though we've got really precise estimates of how it works, there's still an inherent risk on any play of the game. Just, you can't guarantee a win. Now that's completely obvious here, but in the simulation community, particularly my colleagues in the research community, we've focused almost obsessively on measuring, controlling, and displaying error on estimating the mean. In fact, we spent lots and lots of our effort on being able to do that very well, rather than trying to convey the risk in making a decision. And that's going to be my theme in this first one, the difference between error and risk. Okay, so that's our first example. All of us completely understand that here having small error doesn't mean that we get rid of risk. I want to do one more easy example to train you to look at a particular kind of chart. And then we'll do the example that I think is a little more interesting. All right, so suppose that you are designing or trying to improve some kind of an order fulfillment system. So customers order something from you, you have to assemble it or construct it, and you ship it out to them. And you're trying to decide, what should I promise as a delivery date? As a general rule, I should say, how many days does it take for me to get this to you? A number of years ago, Dell Computer in the US used to say, 7 days from when you ordered your computer until it appears on your doorstep. Right? So, you've got to take into account some sort of risk. What is it that you should actually promise? So we build a simulation of our system, and let's start by just simulating 100 order fulfillments. Now I'm going to display the results in a very familiar way, which is a histogram. Right? So a histogram of the time it took us to deliver, to fill those 100 orders. And I'm going to put some additional things on top of that histogram that you probably haven't seen unless you're familiar with an obscure paper of mine on something called the Moore plot. Now, I call these eye chart examples because, at least in the US, when you go to the eye doctor and they're trying to get you a new prescription, they go better or worse, and they try lots of different settings. This is going to be a lot easier, though, because each time we do it, it's actually going to get better. Okay, so there's the result of running the simulation where we filled 100 orders. And the blue histogram there shows that from about 5 days to 35 days for those 100 orders of what it took. Now, I've added some things to this plot. The arrow that goes right down the middle, that's the mean. Right? That's the average time that it took to fill those orders. The other two arrows are at the 95th percentile and the 5th percentile. So of those 100 trials, 90 of them are inside the box, and 5 are outside the box on each side. And just to make it quite clear, I've labeled those, not so easy to see, as likely for the things that are inside the box, and unlikely for things that are outside the box. Now the other thing that's on this chart that's very important are these error bars at the bottom. Those are confidence intervals that say how well have I estimated the mean, the 5th percentile, and the 95th percentile based on the data I've got. So we call this a Moore plot, measure of risk and error. The measure of error are these confidence intervals along here. The measure of risk is kind of that box. It shows what's likely to happen and what's unlikely to happen. Now what I'm going to do is go from 100 orders filled to 1,000 orders filled. And I could ask you if it's better or worse, but you all know that 1,000 simulations is better than 100 simulations, so that's what it looks like when I do that. So better, right? But in what way is it better? So in what way is it better? Well, it's not that the risk has changed at all. The histogram has been refined a little bit. The way it's better is that those error bars have closed in. I have better estimates of the mean, the 5th percentile, and the 95th percentile. But I haven't changed the characteristics of filling orders. It's still variable. It's still from about 5 days to 35 days, right, that it takes me to fill the orders. If I go to 10,000 orders that I've simulated filling, again, now I've got almost no error on those estimates of the mean, the 5th percentile, and the 95th percentile, but the inherent risk is still there. None of us would promise the mean if we didn't want to disappoint our clients. We might promise the 95th percentile as a way to promise something, but none of us would promise the mean, even though the error has gone effectively almost to zero. Okay, so this chart's going to come up in the next slide. All right, so again, nobody in this room, none of us would have made this mistake. We all would have understood that if we were trying to promise, we wanted something out a little farther in the tail of the distribution. So here's a real consulting project that I had a couple of years ago. We're a magazine distributor in the US called Charles Levy Company. And what this company does is they distribute magazines to drugstores and department stores and grocery stores on a weekly basis, weekly titles. So in some sense, it's a single period inventory problem, right? Each week I've got to decide how many magazines to solve, but it's a complicated single period inventory problem because all the magazines don't just go to the same place in the store. They go at the various checkout counters. Some of them go along the main line. It turns out if you're willing to pay a little bit of money, people will reshuffle the stock in the middle of the week, right? So it's not a simple problem to decide what's the optimal inventory policy for each magazine for each store. Maybe somebody else could do it another way, but I did it using simulation to be able to set that. Now what Charles Levy wanted to do was maximize their long-run average profit, and I think that's a perfectly sensible goal because they're going to be distributing magazines week by week for years and years and years, and if they have an inventory policy that says my long-run average profit is maximized, that's going to be the best thing that they can do. So here I think the average really is what you want. Like this is a sensible objective. Now one thing I learned about the magazine business that I didn't know before is that not only do different magazines have different kinds of levels of demand, but they also have very different behavior. So for example, for People magazine, it makes a lot of difference who's on the cover. If somebody who's really hot is on the cover, then you sell lots and lots of magazines that week. And if somebody who's out of favor, then not so many. And that happens across the entire network where you distribute. Something like The Economist doesn't matter so much what's on the cover, right? There's some variability week to week, but the cover is not all that important. So the behavior of these things are really quite different. So I'm going to show you simulation results for two magazines, one of each type. And I'll admit right now, I've tricked it so that these are two magazines who have the same long-run average profit under the optimal restocking policy. But it's one of each type. And I'm going to use Moore plots as a way to take a look at it because we've gotten familiar with that now. So the one on the top, that's something more like The Economist that doesn't have this common cover effect. And the one on the bottom, that's something more like People magazine where who's on the cover matters. So you get a lot more variability in the week-to-week sales. So what we're seeing is the results for average weekly profit across your network. And just to make it a little easier to see, I'm going to put that dotted line in there at 0. Just so we can highlight that, because to the left of that is I lose money that week, which they certainly did. Now imagine as a consultant, if all I had reported to them was, here's your optimal inventory policy, and here's the long-run average profit that you're going to make without saying anything else about the behavior. well, that might not be too bad for a magazine like The Economist, but for something like People, it'd be quite easy to go 3 out of 4 weeks losing money. And what would actually happen? Well, pretty quickly they would decide that the pinhead academic didn't know what he was talking about, and they'd go back to the ad hoc kind of policies that they had used to staff things before. So even when the long-run average is what matters, if we don't convey a sense of risk, if we don't convey a sense of what the actual behavior of that policy will be when you implement it, we really fall short of everything that the simulation can give. All right, so the first way that good simulations go bad is that we forget that we control error through replications and run length in order to measure risk. Because decision problems, at least if they're problems for which you're using stochastic simulation, involve some level of risk. Even when the long-run average is what matters to you, risk tells you something about the actual behavior that you'll see when you implement. Okay, number 2, the ghost of R.A. Fisher. Now, Fisher's actually a hero of mine, even though I'm going to claim we're haunted by the ghost of R.A. Fisher. He's one of my heroes. It's easy to argue that Fisher's work has had absolutely the most profound effect on how people run statistical experiments. Factorial designs, blocking, analysis of variance, hypothesis testing, all of these things trace their roots back to Ronald Alvar Fisher and are still in wide use today. Certainly no engineering statistician would be practicing without these kind of tools. Now, among other things, Fisher thought about agricultural experiments. And agricultural experiments involve a growing season, and a growing season can be a long time. Right? So it's not like running a few replications of a simulation. It's an entire season in order to get your results. So classical experimental design, naturally, given Fisher's point of view, is a structured approach to try to get as much information as you can out of a relatively small sample of expensive data. And that was the context in which Fisher thought about experimental design. But doing simulation is not really much like raising corn. First of all, often, not always, but often individual replications of our simulation are cheap. Right? So we could actually get a lot of them. Response variances can differ substantially across the different settings or scenarios we do. We simulate lots of things that look like queuing systems. We all know that as queuing systems approach capacity, the congestion measures tend to explode. When you simulate those systems, the outputs also get explosively variable to estimate those things as well. So anything like an equal variance assumption, not very tenable in many of the things that we do. Data can be collected sequentially rather than in one shot. We don't have to think about a one-shot growing season. We can think about collecting data, making decisions, collecting more data, doing things in sequence, and learning as we go along. The kinds of systems that we deal with often have lots of factors that we could change. Before we do anything like a designed experiment, we might want to explore those factors interactively, right, to see what's really going on and decide what factors we actually want to look at, as opposed to trying to identify everything that matters up front and develop some kind of designed experiment for that. Sunlight's going to wash me out here. And I argue that we should be driving our experiments more by the error that we can accept in our experiment result, as opposed to the amount of data that we can afford. Because oftentimes we can afford as much simulation as we need. If we thought instead about how much error can I accept for the decision that I want to make, that will often drive us to do more simulation than what we do now, which means that asymptotic results from asymptotic statistics, actually really often apply in what we're doing. They're really quite reliable because we are operating in large sample kinds of regimes. So in practice, I mean, I've taught students for many years and done lots of consulting. How do I really see people doing experimental design and simulation? Certainly some of them do Fisher-like experimental design, but here's what I see more often. Step one is build a simulation model. While you're building the model, you make lots of mistakes along the way, debugging and trying to get it right, but you actually learn something as you're going along. So you don't start the experiment with no knowledge. You actually know quite a bit because of the whole model building process. now you choose an experimental design, and far too often the experimental design that I see is I'll run the default number of replications that the software has coded in it, or I'll do 30 replications because you mistakenly believe somewhere in a statistics class somebody told you that 30 is always enough. And then I'll try some obvious scenarios, some obvious settings that will either confirm what I already thought or make me realize what I thought was not correct, and then I'll try some other things. Now, there's absolutely nothing Fisher-like in that kind of experimental design, and it opens us up to lots of mistakes. On the other hand, there's lots of value to approaching the problem this way, this sort of interactive, playing with the model, figuring out what's going on. It seems like it would be nice if we had experimental designs that allowed us to be correct, but also to work with the model in the way we would like to work with it. So my second demonstration, and I'm really worried about the sunlight on this one, is we're going to run a little example of a simulation that works like that. Now, I realize that's very hard to see, and so I'm going to try to explain what's here. This is the disadvantage of not using somebody's nice software. So this is my mock-up of an interface to, thank goodness I'm not the interface person. And this is a manufacturing systems problem. So I've got 5 work centers that I've called A, B, C, D, and E, and my problem is I'm going to try to decide how much capacity I want to allocate to each of those. And I've got a budget, and I have some ideas about what I could do. It's not a firm budget, so I don't want to think of it exactly as a constraint. And so I've got initially 4 ideas of, I think these would be good ways to allocate capacities. Think of it as number of machines or number of workers or something like that, those centers. Now, when I press go on this simulation, it's going to start simulating these 4 alternatives. Oh, it's looking at cycle time, which is the time to produce your product from start to end. So smaller is better. I'd like to pick the system design that minimizes my long-run average cycle time. That's the goal. So it's going to start simulating them, and eventually it's going to apply a procedure that says, oh, this is not statistically competitive, I can stop simulating this one, and in the end it will have one, and there will be a statistical guarantee that it's the best. Now that's a very Fisher-like type of environment, other than the sequential part, except after seeing the results of those 4, oh, I've got some ideas, now I see what works, I've got some other ideas I'd like to try. I've already typed them in, again, for the reasons I told you before, but they'll be revealed. I say, now there are 4 more ideas I'd like to try and see how they go. And when that experiment stops, I'd like to still know the best one. I'd like to still have a statistical guarantee that I've done the right thing without having to go back and re-simulate the ones that I already started with. And then after I see those 4, oh, that gives me another idea, and I try a few more, and at the end I'm happy and I stop. And what I want is an overall guarantee at the end that I've still correctly picked the best design, even though I've done it in this highly sequential and interactive way. Now I realize you can't much see the numbers here, but you can see the first design is being simulated. It starts out by just getting 10 replicates of each of those. And then it starts sequentially adding replications until it can statistically conclude that one of these is the best. And I made this so it would stop pretty quickly. And so when it stopped, it turns out it was able to eliminate the first, second, and fourth, and it says if you stopped right now, you have a statistical guarantee that the third one is the best. But it turns out, having seen that, I now thought, oh, now I see kind of what works and what's effective. I'm going to try some others. In reality, you would type those in, but I went ahead and put them in advance. Now the most that the procedure will have to do is go back and simulate the one that we thought was the best after we did the first 4. It doesn't have to look again at any of the other ones in order to control the statistical error. Now I've set this up so it's going to run really quickly. It only needs a few replications, and boom, it's done. And now it turns out if I stopped right now, I would have the same confidence level that I have picked the best of those designs. But having seen those, there are now 3 more. I would like to try those and see if I can do a little better. And this will take very little time at all. So this is a kind of a person-in-the-loop optimization, right? You're the optimizer. You're making the decision about what you want to do, but the experimental setting is making sure that you still have a statistically valid conclusion at the end. right? And so congratulations, the last one that you found turned out to be actually the best. You are an optimizer. I think this is what people want to do in a lot of settings. There are certainly settings where you want to do an algorithmic optimization, and I'm going to talk about that next. But this is oftentimes what you want to do. I think what we want are experimental designs that support the way we would like to work with the simulation, but still guarantee that we have a valid conclusion in the end. So the second reason why good simulations go bad is we either use old experimental designs that constrain us from what we really want to do, or I think what happens more often is we use no experimental design at all. Right? And that really opens us to making truly catastrophic statistical errors in terms of the conclusions that we make. I feel like my voice is finally warming up a little bit. You can tell me when I get to George Clooney. Okay, third topic. Simulators need to clean up their messes. So we talked about person-in-the-loop optimization. Now I'm going to talk about algorithmic optimization. So since mankind built its first simulation out of rocks, sticks, and animal dung, there's been a primal desire to treat it as the objective function of an optimization. Right? You build this model. There are things that you can change. We're OR people. We want to optimize it. We want to change those things and find the optimal solution. Here are sort of standard examples. How many and which redundant components should I include in the system to maximize long-run system availability, subject to a budget constraint? Here's the kind of thing we talk about in Chicago all the time. How do I set the red, green, and left turn arrows on the traffic signals to minimize aggregate driver delay on Lakeshore Drive? Oh, if somebody could just solve that problem, we'd be really happy. And more of a supply chain type of problem, decide how many of each product variant I should stock to maximize my expected profit for the selling season. So these are simulation optimization problems. These are the kinds of things that have so many feasible solutions that we really want to approach it in an algorithmic way. Now, simulation optimization is hard. First of all, it's nonlinear optimization. The kinds of things we tend to simulate have very nonlinear effects in them. Nonlinear optimization itself is hard in general. But in our case, the objective function is not something we can write down. It's implicit in the simulation code. We probably have no known properties in many cases, something like convexity. There's no real way for us to rely on that except in very special problems. In a stochastic simulation, this objective function is evaluated with noise. There's statistical error. That's what we've been talking about. So I only get an estimate of what the objective function value is anyways. We tend to work on hard problems that have a mix of integer, continuous, and categorical decision variables. Certainly the ones I see in practice are most often integer and categorical variables and some mix of those kinds of things. And our objective function, it's not like just plugging in values into a linear objective function for an LP. This involves running a simulation which might take from seconds to hours to evaluate the objective function each time that we do it. So how do we solve these problems? Certainly in the commercial software world, there are a lot of meta-heuristics used. Meta-heuristics are these robust optimization heuristics that have been very successful in deterministic problems and we think should work reasonably well in stochastic problems as well. In the research community, ranking and selection, when you can simulate them all. Adaptive random search, when we think about integer types of decision variables. And steepest descent algorithms with gradient estimates if we're talking about continuous decision variables. What I'm going to talk about here applies to all of these. So I don't care which way it is that you're doing the optimization, the way that good simulations go bad, that I'm about to talk about, applies to them all. Okay, so here's our last demonstration. This is a demonstration I use to teach students about simulation optimization. This is a simple optimization problem. X, which is my decision variable, can take 10 values, 1 to 10. So X is along the top here. You get to actually know the true answer before we start simulating. So the true expected value from the simulation is listed there, and it's also the blue diamonds. So smaller is better. This is a minimization problem. So solution 8 is actually the true optimal solution. Right? But when I actually run the simulation, we wouldn't know that. Eventually, I'm going to have estimates of its values and how many replications have been allocated. Now, I'm going to run the simplest possible globally convergent algorithm on this. And here's how it's going to work. On each iteration of the algorithm, 2 solutions will get some additional replications. The one that's currently the sample best, that is, has the best sample mean, and one other randomly chosen solution. Next iteration, whichever one has the best sample mean gets a few more replications, and we randomly choose a solution to get a few. Now, why is that going to converge? Because eventually we'll simulate all 10 of them infinitely often, and so we'll get an estimate of what they are. Even though that sounds simple, it's not unlike a lot of the things that are done in the research community to have these globally convergent adaptive random search kinds of algorithms. Now, these X's along the bottom, when they're sitting along the bottom, that means no simulations have been done of that outcome yet. When that X pops up, that's going to mean I've simulated that one, and the height that the X pops up to will be the value of the average of the number of replications that I've done. So if I've done 10 replications of this solution, that X will be at the height of its sample mean. And of course, that's what we would use to estimate which one's the best. Now, here's what I want you to watch during the course of this algorithm. Remember, you know what the best answer is, and I want you to watch 2 things. On each iteration, which one do I think is the best? That's going to be the X that's the lowest, because I'm minimizing, but not sitting down on this axis, because that means I haven't simulated it yet. So which one do I currently think is the best? And the second thing I want you to watch is, what's the direction of my error in terms of what I think its value is? Remember, its true value is the diamond. That's the true long-run average. Where the X sits, that's my estimate of its value. Okay, so look at those 2 things as it go along. Which one do I currently think is the best? And what's the direction of my error in terms of what I think its value is? This is the last time I'll be... Okay, all right. All right, so here we go. We're going to run global. So I'll talk you through a little bit in the beginning. So in the first iteration, we randomly chose 10 and 3. 3 looks like the best, right? It's got the lowest X. So it's going to get a few more replications, and we randomly chose 2 in the next one, and it got a couple. And we're going to keep going along on every iteration, every time the little hand over there presses the button. The one with the sample best gets a few. Oh, finally we simulated solution 8, but we didn't actually realize that it was the best the first time that we did it. So now it looks like we actually do think that solution 8 is the best. Now we simulate solution 9. Now it looks like the best. It gets a few more. So as we're going along, we're giving the sample best a couple of more replications and randomly choosing one other solution to do that. Now, I rigged this to stop when we would have made the right decision, right? You can see that we're sitting here, we've got the value, we're going to pick solution 8 as the winner, and we've got its value done pretty accurately. Notice we never did get around to simulating solution 1. And if I'd waited long enough, we would have eventually got it, but we didn't actually get there. All right, so what did we learn from this? So what kind of mistakes can you make? Because, of course, you don't get to know the blue diamonds in reality. You don't know where they are. So you have to stop on some metric, and you may have hundreds or thousands of millions of feasible solutions that are in there. So what kind of mistakes can you make? Well, the first is you don't find the optimal solution. Hey, if solution number 1 had been the optimal solution, we would never have even simulated it where I stopped. We would never have known tough luck. That's the way nonlinear optimization is in general. It's very hard to guarantee that you're going to find the true optimal solution. That doesn't trouble me nearly as much as this one. When you do stop, you may not recognize the best solution you actually simulated. There were lots of places along that demonstration where if I had stopped there, I would have picked some other solution besides solution 8 because its sample average was lower than the sample average for solution 8. It's a random process. That happens. Even worse, I eventually picked some solution. What was the direction of the error? Oh, it was always optimistic, wasn't it? Because what kind of solution do I pick as the current best? I pick one whose sample mean is low. And if it's abnormally low, then that's the time at which I pick it. Right? So the error is always optimistic. So I didn't find the optimal solution. I didn't actually pick the best solution of the ones I simulated. And when I implement the solution that I did pick, I have an optimistic idea of how it's actually going to work. You almost want to give up. Right? It's like we didn't do anything right there at all. So this simulation optimization is very, very difficult for this reason. Now, it's really hard to do anything about number one. You can have an algorithm that's provably convergent, which means if you run it forever, then it will get to the right place. But we don't actually have to settle for number two and number three. So I want to talk a little bit about the idea of statistical cleanup. So once the optimization stops, we don't have to be done. There's no inherent reason why that has to be the end of what we do. What has the algorithm delivered us? It's delivered us a bunch of solutions that it's simulated with some idea of how good they are. We ought to view that as the first step in an optimization. The second step is to try to clean up the mess that we've left ourselves. For example, if we can find the best of the solutions the optimizer actually simulated, that gets rid of problem number two. Did we actually find the best of the ones we really did look at? If we can control the error on the estimate of the one that we pick, then we get rid of problem number three. At least, if it's not the best, the global optimal, at least I know how good it's going to be when I actually implement it. So this is not that hard to do. The idea of statistical cleanup says, start with whatever the optimizer gives you, using the observations that have already been generated, and add the smallest amount of additional data that you need to add to give yourself some statistical guarantees. For example, I could add just enough additional data to guarantee, say with 95% confidence, that the selected solution is the best, or within some practically significant difference delta that you get to pick of the best, and that the selected solution's estimated value is within plus or minus delta of whatever its actual value is. This can be done with remarkably simple statistical procedures, and often with very little additional data beyond what the optimizer has already generated. So the third way that good simulations go bad is that we settle for what the optimizer gives us without going the additional step of trying to add some statistical validity to the result that we get. And it's not that hard to do. Okay, home stretch here, last one. Everything I told you is wrong. That is a tough admission to make for somebody who's taught simulation for 30 years. But you'll see why I say that in a minute. Now for here, I'm going to use a stylized example, the infinity queue. This is a queue with plus on arrivals, exponential service, infinite number of servers. Think of it as a self-service system. These are often used to model mobile communications where you want lots and lots of bandwidth. Now this is completely studied. You see it in almost any first course in queuing. And the thing I'm interested in, which I'm going to call Y, is the steady state number of customers in the system. Right? The long run number of customers in the system. When the true real-world arrival rate is lambda c, c stands for correct, the true one, and the mean service time is tau c. This is well known that there's no real reason to simulate this at all. The expected value of the number of customers in the system, the expected congestion in the system, is lambda times tau. That's the arrival rate times the mean service time. That's a well-known result in queuing theory. There's really no reason you would ever simulate an infinity queue because you can solve everything you want about it. But if you'll humor me today, let's think about what would happen if we did simulate this. All right, so as a little thought experiment, what if I didn't know this result, and I had out there in the real world an infinity queue, and I wanted to observe the system, build a simulation model, and estimate the expected number of customers in the system in the long run. Okay, so here's kind of how we would do it, and sadly this is not that much different from what I actually teach students to do. Now I'm going to take one of the hard parts out of the problem. We know the arrival process is plus on, we know the service time is exponential. That, of course, we actually don't know in real problems as well, but I'm even going to take that out of the mix. So now I go out to the real world and I observe inter-arrival times of customers. Right, this is my data collection phase. And I'm going to estimate lambda c, the true arrival rate, which I don't know, by 1 over the average service time, or the average inter-arrival time observed. That's one possible estimator that I could use. I also go out to the real world and I observe customer service times. That is, after they arrive, how long do they stay in the system? I'll call those S1 through SM, and I'll estimate the true mean service time, tau c, by the average service time that I observed. Right? That's not different from what we teach. I didn't have to pick the distributions, but the rest of it seems completely reasonable. Now, there's no reason I would have to observe the same number of inter-arrival times as service times, but I did that here to make the map easier to look at. Okay. Now I've got everything I need to build my simulation. I'm going to run n replications of my simulation. Now, here's the place I'm really going to depart from what we would do. Normally, we'd run each replication for a while, and we would average the number of customers in the system. I'm going to, because this is a stylized model, I'm going to pretend like I run the system a long time, and I just take a single observation of the number of customers in the system in steady state. Then I do another replication, I do the same thing. So I'm just taking one observation from each replication. That's going to make the math work, but the basic idea is exactly the same. So on each of n replications, I observe replication 1, what was the number of customers in the system in the long run, 2, 3, up through n, and then I estimate the true steady-state expected number by the sample unit base. I think we agree, right? This is pretty close to what we would do. Now, there are two things I want you to remember on the next slide, M and N. M was how much real-world data I had to build the model. Right? That was what I used to do my input processes. And N was the number of simulation replications that I did once the model was built. Now, this is such a simple model, as I think you would agree, that it turns out I can compute everything about y bar. Any property of it you want to know is computable. So there are two things I want you to look at. One is, what is its mean value? That is, what is the expected value of the estimator? I'd really like it to be lambda c times tau c. And what's the variance of the estimator? Because that says, how much error is there that's left. Well, it turns out that there's some bias, right? That bias occurs because, hey, my simulation result is a nonlinear function of those parameter estimates, so there's some bias. It's pretty small here. It's a function of how much real-world data I have. If I have more real-world data and I get a better estimate of lambda and tau, then that bias goes away. I'm not so much interested in that today as I am interested in this. What's the variance of that estimator? That's our usual measure of how well I've estimated something from the simulation. And if I account for both the simulation variability and the variability of estimating those parameters, then I end up with two terms. This first term is the one that people like me teach about obsessively in simulation classes. Right? This is our usual measure of error. It's some sigma squared over n. Right? Oh, the more replications you make, the variance goes down as 1 over n. I use that to get confidence intervals, other kinds of measures of error. While the reason why everything I told you is wrong is because I never do anything about this term. This term comes up because I had to estimate the input models in my simulation. Right? Those were all estimates. I didn't know what the true arrival rate and surface rate was, so I estimated those from data. Now, depending on the values of m and n, this could be much, much bigger than that. I can make so many replications that I think I've estimated this so well, and yet there's this huge term out here that I've done nothing about. And look at how simple I had to make the problem to be able to write that down. For any kind of realistic problem that we would simulate, I have no chance of writing down an expression like this to actually see what it is. So I call this input uncertainty. And input uncertainty error, what this demonstrates, can overwhelm everything else. You can think that you know something extremely well, but you've actually been completely overwhelmed by input uncertainty. So what can you do? We actually have in the room Russell Chang, who's an expert on this topic. I hope he won't be too offended by the way that I'm going to deal with it. But here's a simulation-based idea for how you could get a feel for how much input uncertainty is going on in your simulation. So there's the real world, represented by a cloud. In our case, it was an infinity cube. And there's some probability distribution you don't know. So let's talk about the inter-arrival times in our case. You go out and you collect your real-world data, and you use that to fit an input model that you're going to use in your simulation. That's a pretty standard thing that we do. Now, as a thought experiment, suppose that each of us went out and collected our own independent sample of data from that same system. So each of us, there's the first person in the room collected their sample, the next person collected another sample. We would each fit our own input model. We would each run our own simulation, and we would each get somewhat different results. The differences in our results, that's input uncertainty. Right? The fact that Benny gets, get different results is the result of input uncertainty, because we each got a different sample of data. Now, this would be a horrible way to do it. It's very expensive because we all have to go out and collect our own individual samples. But we can mimic this in the simulation using what I'll call empirical world. So I'm going to pretend like the data that I saw is actually the real world. Oh, it's really easy for me to generate multiple samples of that repeatedly, for which I could fit a different input model, for which I could run different simulations. Now, in the research community, we argue a lot about exactly how you should use those results. But a very simple heuristic is do this 3 or 4 or 5 or 10 times, run your simulations at each one, and that gives you a good indication of how much your simulation results would vary based on the different distributions that you could have seen. And unfortunately, sometimes you'll find that's depressingly large, right? That input uncertainty is much, much larger than you would realize. So the last way that good simulations go bad is that we ignore a really big risk, which is the risk due to input uncertainty. Okay, so to close, a few years ago, the renowned statistician Brad Efron wrote a really nice book called Large Scale Inference. And in that book, he gave what he called a simplified history of statistics. So he traced the beginning of statistics as a well-defined discipline to the Belgian statistician Keynote, who applied large census-level data sets to ask important but relatively simple questions like, is the rate of insanity increasing in our population? Then the period that we're all most familiar with, the classical period of giants like Neyman and Fisher and Pearson and so on, they looked at the statistical problem as how do I wring the most information I can out of an expensive, scientifically created data set? And they were masters at getting the optimal statistical inference out of a small amount of data. Efron claims we've now moved into what he calls the era of scientific mass production, when teams of scientists can produce vast amounts of data, and they want to ask not simple questions, but maybe thousands of estimates or thousands of hypotheses simultaneously. And his claim is this requires a real rethinking about how we do statistical analysis. That the sorts of, this was not that what Fisher and Pearson and Neyman had in mind when they were thinking about statistical inference. So this motivated me to think about Nelson's simplified history and future of simulation statistics. So for me, the beginning of simulation statistics was when we started to think about that the simulation language automatically computed statistics for us. Hey, if it's a resource in the model, you ought to deliver me a utilization. If there's a queue in the model, give me waiting times or congestion measures. That made it really easy for us to think about simulation as a statistical experiment without a lot of overhead to get a lot of estimates out of it. Where I would claim we are now is that every simulation language or modeling environment, every well-taught simulation class, thinks of simulation as an experiment, a statistical experiment. It gives you an easy way to manage scenarios, to control the number of replications or the run length, and often just automatically produces confidence intervals on everything, realizing it is a statistical experiment with error. Here's where I think we ought to be going. Experiment design and analysis driven by decisions, driven by the decisions that the simulation model is supposed to support. So I want measures of error and measures of risk, including input uncertainty, to be what's automatically generated, that we don't ever just produce the mean and think that that's enough. I want experimental designs that attain acceptable error or make the best use of the available time that we have. I think we need to stop asking people for numbers of replications. People need to tell us, here's how much time I've got, or here's the amount of error that I can tolerate, now give me results. That's more driven by decision. I'd also like for us to have more statistical designs that support the way we want to do simulation, which is often interactively. Now there's a cost, right? The cost is to do it right, you'll have to collect often much more data than you would if you had done a carefully structured design and experiment, but we can often afford to do that. And it allows us to do the simulation the way we would like to do it. And finally, for simulation optimization, we ought to be using optimization methods that have a convergence guarantee, because I do think that that's really important. but also gives us statistical cleanup at the end. So at least we have a guarantee that we picked the best of the ones we simulated and estimated how well it works. And that's all I have. Thank you very much.
Thank you, Barry. We have about 8 minutes for questions, so I'd like to invite first questions. Mark.
Barry, it's really refreshing to hear an academic talking about simulation being done in this interactive way, which obviously happens a lot in industry, and I think it's also really interesting to see you highlighting something that I completely believe in. People who are doing simulation, all people, the vast majority of people doing simulation these days, whether they're really detailedly trained people who know everything they should know about simulation, or end users who are playing with it for the first time, don't concentrate on actually solving the problem. They spend all their time building the model. Perhaps they spend quite a lot of time producing results, but they don't think, how am I going to display these results in a way that's actually going to cause the person that's commissioned me to really understand what to do and see a way into the problem. So I'm just wondering what you've given us a future here, a way forward, but how do we encourage people to actually think about how to display the results rather than how to build the model?
So I don't have a completely good answer to that, but I'm going to steal a little bit of what I'm going to say tomorrow in the panel discussion, which is, this is one of the things that the field of analytics does better than we do, right? Because analytics is a lot about how do I look at large volumes of transactional data and somehow slice it, dice it, display it so that we can see what's going on. And part of what I'm going to say tomorrow is I think that's the way we should think about simulation, is analytics on simulation output data. So I'm a little bit hopeful that the emphasis on analytics will change people's expectations of what a simulation should give. Right? Their expectations are somewhat set by what we've done historically or what they've seen in the books. I think people are going to expect more. I think they're going to say, no, I want to see that data like I see my, my customer use data or the other sorts of things. And so I don't have a good answer exactly for what we could do, but I think we're going to be forced to do it. I would love to see us be able to interact with our simulation output more in terms of the questions I want to answer, as opposed to a list of performance measures. And that I think would push it. So it's not a great answer, but I think we're going to be pushed that direction.